Bismillahirrahmanirrahim. Hi everyone, thank you for joining this tutorial. Today we will create a digital elevation model. Our tutorial today about interferometry processing with the Sentinel 1A. The goal of this tutorial is to provide novice and experienced remote sensing users with the step-by-step instruction on interferometric processing with the Sentinel 1A interferometric wide swath mode products for digital elevation model generation. Video outline. In fact, we have 5 phases in this video. The first, we have to take a background about our tutorial. The second phase, we will see how to acquire the Sentinel data from the website. The third, we will make a pre-processing for the data. The fourth phase, we will do the interferometry processing by using Snap software. The fifth phase is we will create a contour line with the 2-dimension and 3-dimension by using QGIS software. First of all, synthetic aperture radar is a microwave imaging system. It has day and night operational capabilities and cloud penetrating because it is an active system. The single force synthetic aperture radar contains amplitude and phase information. The amplitude is the strength of the radar response and the phase is the fraction of one complete sine wave cycle. The phase of the SAR image is determined primarily by the distance between the satellite and antenna and the ground targets. By combining the phase of two images after co-registration, an interferogram can be generated whose phase is highly correlated to the terrain topography. It can be done simultaneously by the same satellite with the two radar or two antenna, like the InSAR radar topography mission, or by exploiting the same orbit for the same satellite, or by using the image for two satellites like the case in Sentinel 1A and B. Sentinel 1A and B satellite were launched by European Space Agency. Sentinel A was launched in 2014 and B in 2016 with the altitude 693 kilometers. This figure appears here in the top of the right of screen. Show the cover for Sentinel 1 and A and B and the mode for this cover, and the second figure explain the modes for the Sentinel. Actually, the Sentinel 1 have 4 type of mode. This appear in this figure. The first one, extra wide swath mode, interferometric wide swath mode, strip map mode, and wave mode. The interferometric wide swath mode is the main acquisition mode over land for Sentinel A. It is contains of three subswaths are labeled with the red color. Each subswath image consists of series of bursts. It are labeled with the white color. So the interferometric wide swath mode acquires data with 250 kilometers swath at 5 meters by 20 meters spatial resolution single look. After download images from Sentinel, it will be written like these samples. This is referred to Sentinel name of satellite Sentinel 1A, the mode, single look, complex, and the path and the date. Now it is important to take an idea about a synthetic aperture radar interferometry. The basic idea behind synthetic aperture radar interferometry is the combination of information provided by two different radar images which have a known distance, named the perpendicular baseline. Like I mentioned, this perpendicular baseline between satellite, between antenna, maybe between two satellites, or between two time for taking this image for the same satellite, or between this perpendicular distance for the SRTM. So based on the positioning of both satellites and their perpendicular baseline, three-dimensional information of the Earth's surface can be retrieved by the different path length of the radar backscattering signals from a surface as received by both antennas to generate digital elevation model. The processing for interferometry is appear in this figure. It starts with the co-registration to co-registrate the both image master and slave image for the study area. After that, this is the processing until range Doppler terrain correction to create an accurate digital elevation model. So now we will go to phase 2, Sentinel data acquisition. It is important to mention that we can get the data from two sites actually. The first sites from the Copernicus of Access Hub, this from European Space Agency, and the second can take from Alaska satellite facilities. Actually, this Alaska satellite facilities is so important to get our image or our data, because it's have a lot of helpful actually tools to help us to get a suitable image. So first of all, after we open the Alaska satellite facilities, we create an account for this and go to study area, specific study area, and press in this button to determined our study area here. Now we see is loading for this website to show to us the how many image we have for this place. So we can use this filter is contain the start for the date that for acquired. Maybe we can choose any date, and the end of this date when we was to take image between the period from this. Also this contain the type of polarization, also contain the mode for acquiring for image. So this is so important to choose our suitable digital elevation, our suitable image. So after searching we now get a lot of image for the study area. Actually we can choose any image and choose like we will consider this like a slab as master image, for example, and we after that we will choose the slab image. There is an important tool here that is baseline tool. This is so important to choose the suitable slave image for the master that we choose any image. We just press the button, it will be appear loading this figure that contain actually our master image with all the image that acquired for and the places for the satellite to when they acquired the image. So we can see here how the image here appear with the temporal resolution this day and perpendicular baseline, and appear all the image with the their perpendicular baseline and their temporal resolution. So now we can choose the suitable image from this. We have strategies about the choosing. This our image. This is with the labeled with the red color. It is with the 0 meters and 0 day. We have many choices, but to create an accurate digital elevation model is important to get a small temporal resolution and the perpendicular baseline can be the tolerance between 150 to 300 meters. So the most important, the time of getting the image, it is important, especially with the land of or study of area that covered by vegetation. So we here appear the master image, and we will choose this slave image. When we choose the two image, we can press here in this button to download our master image, and also press here to download our slave image. It will appear here in downloads. After that we will press in this button. After that we will press in this button and this button to download our product to do pre-processing. After that we will create digital elevation model from this image. Actually I already download this image because it take a lot of time. So we now go to the phase 3 pre-processing to make our pre-processing for our product. That is important to do our pre-processing, like we will make a radar radiometric calibration and dippers for this image both. After that we will make speaker reduction in this stage. So first of all we will go to the snap software to open our snap software. This is so important software. It's a Sentinel application platform. It's from European Space Agency. Actually we can open our product. We can open our product by press file, open product, go to where is we save our products. Actually we have these two products for our study area. Now it's appear here, and with the world view is appear is for the study area, for our study area. So now we will start with the first step for the radiometric calibration. It is we wait to download. It's important. So now we will determine the first image and make calibrate by radar radiometric calibrate. It will be written like this, and this we will choose vertical polarization. So after that we will run. It's take a time actually. Now is done with this 3 minutes and more 3 minutes. Close this. The product of after reduction, radiometric calibrate for the first images appear here. So now we will make calibrate for the second image by radar radiometric calibrate. Same, choose vertical. Okay, we press run. It takes some time. So now it's done with the more than 3 minutes. We close this. The products is appear here. So after that we will do a speaker reduction. Actually, to make speaker reduction we have to make our product like remove all the semilines between the parts. So we determine the first product. After that go to radar, Sentinel one tops, and to D burst. We have to remove this semiline for this product. We press run. It also take time. Now it's done. Actually we close this dialog box and go to the second product, radar, Sentinel one tops, deburst. To remove also same, press run. Also take time. Now with the more than 1 minute, so close. After that we will determine the last product and make speckle filtering for our product by press speckle filtering, single product speckle filtering. Okay, now we will choose this. It's appear here vertical only. So press run. It's also take a time actually. Okay, so we change this name. So now after we finish our speckle reduction, actually we will exit from here to go to close the product, to go to our slides. Okay, now we will go to our slide to see the second, actually the next step for our tutorial. The next step for our tutorial is about interferometry processing. Interferometry processing is contain a lot of many processing that we will do with the image after pre-processing. That start with the co-registration. After that we will make interferometric formation. After that we will make the burst and Goldstein filter and multi-looking filter. After that we will unwrapping phase that contain export to SnapView and import and unwrapping, and after that import. After that we will make subset for our product. Then we will phase to elevation to convert all the rainbow color to a metric value. After that we will make Doppler terrain correction. So we will start with our interferometry processing. Actually now it's take a time to download actually. So this our product now, it's appear here for study of area, and we can make our processing with our. So the first of all we will make a co-registration to co-registrate both master and slave image. So first of all we will press radar co-registration with the ESD. This box dialog box will appear here. This the red one is the first image. This the second one should be second image. So tops are split. In this bottom we will choose the which type of mode want. We will choose this interferometry wide swath one with the vertical polarization. We have to reduce the burst for this image between 5 to 8. Also we do same thing with the second image. This apply orbit and back geocoding. This is as we will use as RTM, like a reference digital elevation model. We will choose nearest neighbor. After that enhancement. Okay, so and it will be right. This can be right like this. We remove this. Okay, underscore and remove this to make our project is will be written like this. So just we should to make sure the first one image, the second image, this pairs with the 5 to 8, second also. So just press run to make our stacks, so it's take a time actually. Now it's appear our stock. We close this product, our stack. Now after that we will format the intro program. So we go to the radar Interferometric products, after products intro program formation. Okay, so press run. It's take time actually. Now okay, it's done. Now our product is here. The intro program was formatted. So after that we will remove sublines between the pairs. So go to radar Sentinel 1 tops and Sentinel 1 tops dippers. Okay, run. It's also take time actually. Okay, now after remove the semilines, so we close this product. We no need for this product. Let's make the laptop so heavy. So now this our product. After remove the sublines, we have to apply our Goldstein filter by radar Interferometric filtering spectral Goldstein phase filtering. So now will be like this. Okay, after that so important this filters for our unwrapping phase to help us for our unwrapping phase, the next phase, next processing. So press run. It's take time. Now is done. So now we have the product before make Goldstein filter. Actually we can open the product. This is our product with the noises actually before applying Goldstein filter, and this our product after applying. We see we reduce many noises from our intro program. So Goldstein filter is so important for our processing. So after that we will close this product. After that we will make multi-looking filtering. Actually it's from radar SAR utilities multi-looking. Okay, so press run. After this filtering, we will make unwrapping for our product. So determine the product. After that we will go to radar Interferometric unwrapping. We will export our product to SnapView to make unwrapping there. So this our product, and we will write our product in the okay, we will write this. Okay, after that is changed to topography. So after that we will press run to our to make our product to. So after we export unwrapping to SnapView and make unwrapping and import these folders or products, it's appear here. We can open our new product that is unwrapping to see this our product after applying all the filters and some operators, unique operators, to make our filters now our intro program. And this actually the digital elevation model but is not with the metric value. Now all the elevation is represented by the rainbow color now. So after that we have some noise in the edge. We have to remove this noise by making the raster subset. By raster subset, just remove this edge actually to make our products nice. Okay, so it will be just press OK. After remove this noise, so after that we determine our product to convert to elevation. Actually this rainbow color we have to convert to elevation. So we will press radar, interferometric products, fast to elevation. It will be convert with the we will compare with this RTM and nearest neighbor and press run. Our product appear here now. It's have elevation. So this our digital elevation model before make the Doppler terrain correction. Now each pixel has a metric value in detecting it is high above sea level. So after that we will make a correction, terrain correction by radar, geometric terrain correction, range Doppler correction. So we will make some this by choosing nearest neighbor and this 15 digital elevation model. After that we press run. Actually it's take time. So now it's our digital elevation model. It's appear here. After make terrain correction, we can open our digital elevation model is appear now. Like I mentioned, each pixel has a metric value over the sea level, and we actually notice some noises here because some problem with the weather conditions or by unwrapping processing. A lot of things that is a control about generate a digital elevation model. It is important to mention that our digital elevation model, we can compare or see the accuracy for this digital elevation model by compare with another digital elevation model that have a globally validity like SRTM or W13. A lot of there is many there are many digital elevation to compare, or we can compare our elevation in this model with the ground control point for any study area that we will choose. So now we can export our digital elevation model to Google Earth by file export view as Earth KMZ. So we will okay, so we will choose our export this our file like elevation. So now we export our file for our to view our digital elevation model. We go to the representation of our digital elevation model. Actually, this our digital elevation model is represent in Google Earth, how it's appear and for this study area. So now we will go to another actually to return to our snap view snap software to compare actually our digital elevation model with another one. First of all, we have this in snap our digital elevation model. We have to download the SRTM like a reference for our digital elevation model. So we can download this SRT from USGS actually to download SRTM for our study area to validate from our digital elevation model. So now we will go to study area and specific the study area here. The coordinates will appear here for the any place we can take as a digital elevation model from SRTM. So we press dataset and looking about the digital elevation with the SRTM. We press this SRTM with the 1 arc second, so we will see the result for this. Actually, it's appear two product for our study area. Here we can see the first one and second one, and we can press actually this is the footprint for the study area we can download. And so to download this SRTM digital elevation model from SRTM, just press and download this button. After that, we will use this digital elevation model to compare with our digital elevation model. So actually it's take a lot of time. I already download this digital elevation model, so just I want to open it from where I put actually. So file, open a product, go to the SRTM digital elevation model from SRTM, this here. So open a product, it's appear here. So our digital elevation model, it's appear here actually. Sorry, this for SRTM, digital elevation model for SRTM, and our digital elevation model here is appear here for study area. Actually, to make a comparison for our study area or for our digital elevation model that is related with any area, we can, there is a helpful tool in Snap software. It is pen manager. Can we determine some places with this tool actually to take the coordinate. Here it's appear in the button coordinate and with the longitude and the elevation for this point. And by depending about the by depending of the coordinate, we can compare with the digital elevation model from SRTM. To make same this actually, we can see this pen manager. It's appear here the coordinate and longitude and latitude with this appear here in the staple. Also we can open the SRTM and make some places by choosing by pen manager actually to check our digital elevation model. So this an idea, we take an idea to check the validity and the accuracy for our digital elevation model. Now we will go to the next phase. We will go to our slide to see next phase, that is phase 5 is by to generate a contour line and a digital elevation model with the 2-dimension and 3-dimension. Actually this is can be done by the QGIS software. So we go to open QGIS software. So now it's open this QGIS, and we will open open our digital elevation model in this QGIS. It's appear here. So this by drag from the where I put by drag the digital elevation model. So this our digital elevation model in QGIS. Actually we have a lot of tools in QGIS we can use. The first important tools that is web, that from web can go to QGIS to 3GIS export actually. But before that we have to change the project with this pseudo marketer. Okay, apply. Okay, so after that we can export this by web Q to 3GIS QGIS. It will appear here with the with our product. This is our product actually. This is with the digital elevation model for our study area, and this 3-dimension actually. This with the 1-dimension, sorry, 2-dimension. We see how it's because it's a flat area, a desert, not many different or a big difference between 3 dimension and 2 dimension, because it's a flat area we see this. So we can use some tools actually to make this is nice, by go to scene setting, by increase the exaggeration for maybe 25, and vertical shift maybe also 25 or 20. We can apply, we see we can reduce the with the 10. Okay, we can see okay, so now we see our digital elevation model. It's appear here with the a new exaggeration. We can use a new exaggeration actually. Yeah, so it's appear here our digital elevation model. It's important to mention that this 3 dimensional our digital elevation model, every point here have a coordinate and elevation here. It's appear here when we choose any place. It will appear the elevation and coordinate for this point. So this our digital elevation model, 3 dimensional our digital elevation model with the coordinate and with the elevation for every point here in this place when we specific our digital elevation model. Now we return to appear our digital elevation model. We want to put to change color or to make is so nice. We can press here to change the color. There is some choices here. If you anyone to create any color that you want, we can apply this color with our digital elevation model. It's appear here like we see here, or we can create our own color by create a new color. So we can create this color actually by using this. The first place is for the low area we can, and we can by double click another place to choose the area that is higher this area, and double click in another place to choose a unique maybe unique green, and after that the last one maybe can choose the dark clean green, sorry, to represent the higher places. So we can okay, and we will quantine choose these choices, and we can increase the classes to make our digital elevation model so nice. So after that we will press OK. So this our digital elevation model is represent like this, and we can choose another color by using the color from for example like mega, like this, have a lot of kind of colors, and it can represent our digital elevation model. So these properties also we can make a hell shadow for our digital model. So we can apply hair shadow for this digital elevation model. It's appear here for the desert area. We can export this by web QGIS, 3GIS. This our digital elevation model with hell shadow actually is become so nice with the when we this is this 3 dimension, and this with the 2 dimension it's appear here. Also we can exaggerate this we can increase exaggeration to make is it so nice, or so appear actually when we make this exaggeration to our digital elevation model. So now this our digital elevation model with the hell shadow. So after that actually we can create a contour line for our digital elevation model by press this in contour line and choosing the interval, change this interval to appear is so clearly. Okay, so by choosing this contour line, and we can change the color from here as we like for our digital elevation model to create a contour line. So we can it's appear here, so apply. Okay, so this our digital elevation model with the contour line. Also we can export for to represent it in web. So now this our digital elevation model with a new color and with the contour lines and it's appear here like to represent all the elevation for this place with the contour lines and with the 3 dimension shape. So this is our digital elevation model. So we will close this and return to our QGIS. So now this our digital elevation model with the contour line and represent by 3 dimension and 2 dimension. So this our digital elevation model. Every place here have a metric value with the coordinate actually, and this can represent by 2 dimension and 3 dimension for this place. So thank you very much, and I hope this video is you are get a benefit from this video, and thank you very much for all your time.